So, good morning, everyone. We'll be having a session for week 12 where we'll discuss the assignment solutions for week 11 and li- like sample problems for week 11, week 12, right? So, we'll start with the assignments solutions for week 11. So, for the first statement or question, choose from the following statements that are not true corresponding to nonlinear optical medium. The refractive index in the medium changes with the light intensity. Option B, the speed of light in the medium doesn't change with the light intensity. The frequency of light can be altered by its passage through the medium. Two beams of light in the same region of the medium can have no effect on each other. So, what options are correct regarding nonlinear optical medium? Is it with the first option saying A, comma C and D, B is telling only B, C telling B and D, and D telling A and C? So, with the first statement, the refractive index in the medium changes with the light intensity. Second, sorry for the camera. So, for the intensity, it's not a correct. Option 2 being the speed of light in the medium doesn't change with light intensity, it is correct. Option C, the frequency of light can be altered by its passage through the medium, so it's not correct. The two beams of light in the same region of the medium can have no effect on each other, so it is correct, right? So with for this we can say that option B and D are the correct statements, right? Now moving on to question 2, assertion. Nonlinear behavior can be exhibited when light travels in free space. Reason is that linearity or nonlinearity is a property of the medium through which the light travels. So we'll look into it, that is the assertion correct or not, and the reason is correct or not, and is the reason a correct statement justifying the assertion. So we can see that nonlinear behavior is not exhibited when light travels in free space, right? So the reason is what? Linearity or non-linearity is a property of medium through which light travels, rather than a property of light itself, right? So with this we can say the assertion is a correct like incorrect statement, and the reason is also an incorrect statement. So for this option D, both assertion and reason are wrong. Question 3, general equation of the polarization is given by which of the following statements? So we know that option A is the correct one, saying that P equals to chi of 1 into E plus chi of 2 into E2 plus chi of 3 into E3. Okay. For question 4, which of the following is not a quadratic nonlinear optical response? Is it option A, second harmonic generation, option B, frequency of conversion, option C, self-phase modulation, and option D, optical parametric amplification? So according to this quadratic nonlinear optical response, self-phase modulation is not a quadratic nonlinear optical response, right? Due to which this option is the correct one for this question. The sum frequency generation of two laser lights of wavelengths 1 nanometer and 532 nanometer will appear at what frequency? So the generated sum frequency mu3 is equals to mu1 plus mu2 is equals to c by lambda 1 plus c by lambda 2 gives us a c lambda plus lambda 2 lambda 1 and lambda 2, right? So according to this, the corresponding wavelengths lambda 3 is equals to c by mu 3, right? Which gives us lambda 1 lambda 2 by lambda 1 plus lambda 2, right? And thus we have the values of lambda 1 and lambda 2 as 1064 and 532, right? So we can put it here 1064 into 532, 532, thus giving us the value of 355 nanometer, right? So what we did basically, we basically did the sum frequency generation of two laser lights with the formula of mu3 is mu1 plus mu2, which gives us a c is c by lambda 1 plus c by lambda 2 is equals to c lambda 1 plus lambda 2 by lambda 1 plus lambda 2 by lambda 1 into lambda 2, right? Which gives us the corresponding wavelength lambda 3 as c by mu 3 which gives us as lambda 1 lambda 2 by lambda 1 plus lambda 2, and we are putting the values of lambda 1 and lambda 2 as 1064 and 532, so we are getting it as 355 nanometer, right? So moving on with the next question. For question 6, we can see that we have to match the following models with their respective uh, nonlinear output generations. So for that, we can see, we can look into it as for option 1, right? option 1 we can say like it is doing a second harmonic generation. How we are telling that? We can tell that as the input wavelength is 1.06 while the output is 530, which is uh, twice, right? So the second harmonic generation. For option for statement 2, so as we can see that we don't have to go further, we can just solve it out. So option 2 is a difference frequency generation, as by the difference of these two only we will be getting 0.96 micrometer as a result. This is B, this is D. So with option 3, D is a sum frequency generation, right? And for option 4, it is a third harmonic generation, right? So it is a third harmonic generation. So for this statement, we can see that option B is the correct. Just a minute. The half-wave or switching voltage for a transverse field focus modulator using lithium niobate at a wavelength of 632.8 nanometer, where the value of the appropriate electro-optic coefficient is 6.8 picometer per volt, is what volt? Assume the crystal is 40 millimeter long and 1.5 millimeter deep, with the electric field applied across the short dimension. The refractive index of the crystal is what? So refractive index of the crystal is given. We just need to find the value of the electro-optic coefficient. The V pi we have to find out, right? So what we can see, so we can put the values, and now we know by the formula as V pi equals to lambda d by r n cube L, right? So lambda we know as 632.8 into 10 to the power minus 9. D is 1.5 into 10 to the power minus 3. And 6.8 into 10 to the power minus 12 and 2.2 whole cube into 40 into 10 to the power minus 3, right? So V pi we are getting as lambda d r n cube L, r n cube L, right? So lambda is we are getting this, d is we are getting this, r is also okay, n is also given as this, and L we have this, right? So upon solving this, we'll get it as 327.7 volts. So upon solving it, we will be getting as 327.7 volts. Okay. Now moving on with question 8. In question 7, the modulator is used in one of the arms of the Mach-Zehnder interferometer. The minimum bias voltage required to get the output intensity I out equals to 1 by 2 I naught is what volts, where I naught is the output intensity when V bias is equals to 0 volts. Right? So we know that output intensity of an interferometric electro-optic intensity modulator is I naught by 2 1 plus cos del phi, where I naught is maximum intensity when phase difference between light waves in two arms is 0, right? So this is the definition, and del phi equals to pi V bias t by V pi, right? And we get that I out is equals to I naught by 2 1 plus cos del phi, where it is given as I naught by 2 is given. So cos cos del phi is equals to 0, del phi equals to n pi by 2 equals to pi V bias and t by V pi. So from the previous question, the answer which we got of V pi is 327.7. We can put this same here, right? So and V bias three 27.7 by 2. So considering n equals to 1, V bias is equals to 163.86 volt, right? So we know that V bias is equals to 163.86 volts. So the minimum bias voltage which is required, okay, just a second. Uh, so yes, so with this we can say that the V bias will be 163 point, I'm sorry, V bias is 163.86 volts, right? So now moving on with the next question. Consider the below given optical parametric amplifier. Identify the correct option. So we are having here an omega pump, omega signal, getting it a omega idler, omega pump, and omega signal. So here three options are there. So four options are there: W pump greater than W signal, W pump equals W signal, and W pump less than W signal, or all of the above. So this condition will be occurring when when W pump is always greater than the W signal. So with this, now we can move on to the next question. A pulsed laser beam of wavelength 620 nanometer propagates through a CS2 Kerr cell of length L 10 centimeter, and the effective cross-sectional area A is equals to 0.01 millimeter square. So CS2 has a Kerr index of 3.99 in 10 to the power minus 19 meter square per watt. The optical power P pi that is necessary for the light to undergo pi phase shift due to self phase modulation is what kilo, right? So for this we can say yes. So we know that the phase shift incurred by an optical beam of power P and cross sectional area A is given by del phi 2 pi by lambda into P by A L is equals to pi, which is given, right? So where L is the length of medium in which light travels, and P is lambda A by 2 into L. So this is the formula. So P is basically lambda A by 2 into L. Now the effective cross-sectional area A is equals to 0.01 millimeter square, right? So this is the effective area, cross-sectional area, which is getting us 10 to the power minus 8 meter square. And now the P is 620 into 10 to the power minus 9 into 10 to the power minus 8. So we are getting the formula from here only, right? So we are getting the formula from here only. So 620, 10 to the power minus 9, 10 to the power minus 8. Lambda it is there and A is there. Divided by 2 into 3.99 into 10 to the power minus 19 into length is 10 to the power minus 1, as L is 10 centimeter and N2 is 3.99 into 10 to the power 19 meters square, right? So for this we can get it as 77.7 kilo. So solving this, we can get the answer as this, right? So now we will move on with some sample questions for week 12, right? So for the first question, the below frequency shift observed in an optical fiber provided n effective is equal to 1.6 and the sound velocity is equal to 4540 meter per second for a pump wavelength of 1.5 micrometer is what, right? So for that the given wavelength lambda p is equals to 1.5 micrometer, n effective is 1.6, VA is equals to 4540 meter per second, mu b is equals to 2n effective VA by lambda p, which is giving as a 2 into 1.6 into 4540. So 1 minute. So now we get the lambda p as 1.5 into 10 to the power minus 6, right, which will be giving us 9.68 into 10 to the power 9 hertz, right? So what we are getting, the so basically the frequency shift, right, of Brillouin Stokes waves mu b is 9.68 gigahertz, right? So option A is the correct answer. Now consider the instructions for question 12, 13 and 14. Consider a single mode fiber SMF 28 with an attenuation constant of 0.18 dB per km and effective area of 100 micrometer square and a non-linear Kerr index of 10 to the power minus 20 meter square per watt. So question 12 says that the optical attenuation coefficient in Nepper per meter and the effective length of the fiber are Nepper per meter and kilometer respectively what? So we can say it as Alpha is given as 0.18 dB per km. Alpha 4.34 is given as 0.18 into 10 to the power minus 3, 4.34 Nepal per meter, right? So the optical loss is equals to 4.15 into 10 to the power minus 5 Nepal per meter, right? So we can say from here 1 by alpha is equals to 1 by 4.5 into 10 to the power minus 5. ठीक? So the effective length, right? So the effective length over which the nonlinear phase accumulates is equal to 24.11 km, right? So this is the one. So we have the loss as 4.15 into 10 to the power minus 5 and the effective length as 24.11, right? Now question 13. One sec. So question 13 is saying that assuming a launched power, right, of 100 milliwatts at a wavelength of 1.5 micrometer, the accumulated nonlinear phase phi NL will be what radians, assuming that alpha into L is much greater than 1 up to 1 decimal range and range is 0.5 to 2. Okay. So here we can say as we are given with the A effective area of 100 micrometer square, right? And then lambda is 1.5 micrometer, P naught is 100 milliwatts, N2 is 10 to the power minus 20 meter square per watt, and alpha is 0.18 dB. So phi NL is equals to 2 pi by lambda N2 by A effective P naught 1 by alpha, right? So we can put the values here as 2 pi by lambda. Lambda is basically given as 1.5 10 to the power minus 6. N2 is given as 10 to the power minus 20. A effective is given as 100 into 10 to the power minus 12 and 10 to the power minus 1, and alpha is given as 0.18 into 10 to the power minus 3, right? So these are the ones which are given. So by solving this we can get the nonlinear shift of 0.321 pi, which is exactly exactly around 1 radian, right? So for the next question, if the Raman gain coefficient of the above fiber Gr is equals to 6 into 10 to the power minus 14 milliwatt per watt, and the effective length of the fiber is used in an amplifier configuration, the total gain would be what? dB, right? So the Raman gain Gr is basically given as 6 into 10 to the power minus 14 meter per watts. Air effective is 24.11 km. If is equals to 100 milliwatts and Gr is equals to exponential of A effective. So for this, we can have the formula as 6 into 10 to the power minus 14 by 100 micrometer square, 100 milliwatts into 24.11 km, right? So this, after solving this by converting all the decimal places a to a preferable one or a reference one, we will get the answer as 6.28 dB, right? Now question 16, assertion A, the stimulated Billoy scattering is useful for optical sensing applications. Reason is when highly coherent light interacts with the acoustic phonons, it results in Stokes back reflected signal intensity. Reason 2 is it generates acoustic phonons in highly coherent light with increased incident power, increasing the transmitted light intensity. So Billoy scattering is useful for the optical fiber sensing, right? Strain and temperature. So applications due to generation of Stokes backscattered radiation as a result of light light interactions with acoustic phonons. Such backscattered radiation is useful for sensing applications. So with this, we can say the A is correct and R1 is the correct reason for A, not R2, right? Just a second. Okay. Now we'll move on with the next question. Choose the correct order in terms of the scattering coefficient at room temperature. Option A says the Stokes scattering is greater than the anti-Stokes scattering, and which is greater than the Rayleigh scattering, and further on there too. So for option D, Rayleigh scattering is much greater than the Stokes scattering, which is much greater than the anti-Stokes scattering, right? So why is that? So Rayleigh scattering is elastic collision with higher scattering coefficient compared to Stokes process, followed by anti-Stokes scattering. So in the Stokes process, the scattered signal frequency decreases due to what? Due to the energy transfer to the vibrational states mu naught and mu 1, and in anti-Stokes process, scattered signal frequency increases due to annihilation of molecular vibrational mode. So with this thing, we can say that Rayleigh scattering is much greater than the Stokes scattering, which is much greater than the anti-Stokes scattering, right? Now for the next question, which of the following scattering is not an example of inelastic scattering? Is it Stokes? Is it Rayleigh? Is it stimulated Billow or anti-Stokes? So what is an inelastic scattering? Any scattering process involving energy transfer corresponding to a change in frequency from input frequency is called inelastic scattered, right? So basically stimulated and Brillouin scattering are examples of inelastic scattering. This one, this one, this one are of example of this. This one is not an example, right? So this will be the correct answer. So next question, which of the following processes involve energy transfer with molecular vibrational modes in the host medium? Is it Raman, Rayleigh, Brillouin, or all of the above? So as we have discussed in the 17th question, Raman is the correct one for this statement. So Raman is the process which involves energy transfer with molecular vibrational modes in the host medium. Moving on with the 20th question, which of the following processes involve energy transfer with acoustic phonons in the host medium? Is it Raman, Rayleigh, Brillouin, or all of the above? So we know we have discussed in the 17th question. See, for this, Brillouin is the one which involves energy transfer from acoustic phonons in the host medium, right? So, so basically this is the one, all these 20, 19 and 18 are referenced from the 17th only, where we have discussed in pretty much detail how these scattering things are working. So basically Rayleigh scattering, in terms of the scattering coefficient at room temperature, the Rayleigh scattering is much greater than the Stokes scattering, which is parallelly much greater than the anti-Stokes scattering, right? So, so with this, we will be ending the 12th session. So thank you guys for joining.